Hello. So today we're going to learn about supervised learning. We'll start off in this session talking about general principles, and in the next two lectures we'll talk about classification and regression. As we discussed last time, supervised learning is a machine learning technique that can be used to build models to predict known variables. Today we'll cover the general principles of supervised learning, overfitting and underfitting, why you might not want to use all your data to build a model, testing sets, training sets, and validation sets, and cross-validation. We want to make sure that we build a model with the right level of complexity. We don't want a model that's too simple or too complicated. Instead, we want a model that's just right. But how do we define something that's just right? Well, we want a model that'll give you accurate predictions on new data that was not used to build the model. So how can we tell if we're overfitting or underfitting? Well, by this definition, we have to be able to test our model on data that was not used to build the model. So this is how we do it. We take all of our data and we split it into a training set and a testing set. We use the training set to build a model. Then we can take the input variables from our testing set, plug them into the model, and get predictions for the output variables of those observations that are in the testing sets. Then we can compare the output variables of the testing set with our predicted output variables in the testing set. And through this comparison, we can calculate the accuracy of the model. In biology, we often analyze all our data, but this should demonstrate that sometimes it is useful to save some of the data to test to see whether our models are accurate. What does this look like in terms of the data tables that we discussed in the previous course? Well, recall that our original table has observations as rows and variables as columns. When we split our data set into a training set and a testing set, what we do is we split that table into two separate tables. These tables have the same column headings, however, they have different row headings. This is because we randomly allocate observations to be part of either the training set or the testing set. Critically, there should not be an overlap between data that's in the training set or the testing set. So if observation 1 happens to be in the training set, then it should not be in the testing sets. One question you might have is, how do we determine what the best model is from the training set? Well, sometimes we use the following procedure. We take a training set and we split it further into an even smaller training set and something that we call a validation set. Using the smaller training set, we can build a bunch of different alternative models. Then we can take the input variables from our validation set, plug them into these alternative models, and come up with different sets of predicted output variables from our validation set. We can compare our predicted outputs with our known outputs, and from there, we can pick the model that is most accurate on the validation set. Then this model is the one that we use to find our final accuracy using our testing sets. It's important to have a distinct validation set and a testing set because we want to make sure that our model not only doesn't overfit the training set, but we also don't want our model to be overfit to our validation sets. Finding out how much of your data should go into your training set, testing set, or validation set is more of an art than a science. You need to make sure you have enough data in your training sets and testing sets to be able to build good models and evaluate whether the models are good. Often you do a 1/3 and 2/3 split or a 1/2 and 1/2 split. Another useful approach is called cross-validation. This is especially useful if your dataset isn't large enough to be able to have substantially large testing, training, and validation sets. In cross-validation, you take all of your observations and you do different splits between the training set and testing set. For each of these splits, you can measure the accuracy of your model on the test set. So now, instead of having a single value for the accuracy of your model, instead you have a bunch of different accuracies given different splits between your training set and your testing set. You can draw this as a histogram. Today we covered lots of general principles of supervised learning, such as overfitting and underfitting, training sets, testing sets, and validation sets, and cross-validation. Next time, we'll cover how to build a classifier.